What's up guys, Javier from That Racing Channel. Today's video is a special one for the TRC family. The TRC Sequential Evo is one of the most iconic cars in our channel's history. In today's episode, we're tearing down the 4G63 that's been in the car since 2007. We're here with Jay from R's Garage to see what kind of shape it's in after all those years of abuse. We've raced this car hard over the past 17 years with over 26,000 miles, pushing around 1,000 horsepower, thousands of street pulls, and hundreds of races. We believe this to be one of the longest running 1,000 horsepower 4G63 engines of all time. This Evo's been such a big part of TRC's history, and we're so excited to share this moment with you. So let's see what we discover throughout this engine teardown.
Hi, I'm Jay from R's Garage. Today we're going to take apart this Mitsubishi Evo 9 engine. Now this isn't just any Evo 9 engine, this is the engine out of TRC Evo. Now this engine was actually assembled back in 2007 by a gentleman named Ronnie Crawford, and I had the luxury of meeting Ronnie Crawford in the early 2000s because he built an engine for me for my Mustang, and we got to have a fair share of conversations. And Ronnie is passed on now, but he was a man that was sought after for his work. He was from the old school. He put a lot of attention to detail and tried to share his wisdom with you to keep you out of trouble as a racer. So it was a really neat experience to work with him, and it's a neat experience to have what I would consider the longest running test case of low compression versus high compression, because this engine makes a minimum of 34 pounds of boost. At a minimum, they generally run it at 45 to 50 PSI, and it's been alive this entire time. So the head gasket had been changed once. They created some coolant pressure while racing it at a half-mile event years ago. They put a head gasket on it, some fresh for valve train at the time, put it back together, traded hands. My brother owns it now, and it started to gum up a spark plug. So the engine's at the end of its life, but a lot of people like to say, you know, that engine owes me nothing. Well, this engine has been together, tons of run time, tons of fun time, and we're gonna peel it apart, examine some components, and see if we can find some of the old man's tricks. So come along. So before we get the timing belt off, for those of you that aren't savvy on the 4G63, this is kind of the evolution of the Evolution engine. The early ones were fixed intake cam, fixed exhaust cam timing. This has a MyVac system, so it can advance the intake cam. It's got a fairly unique trigger pattern. So it's got this optical Hall sensor and very few teeth. Most modern triggers are like 60-2 or 36-2, a lot of teeth on the crank trigger. And this is a fairly simple 4-tooth program, 4-cylinder engine. And I tried to make sense of it in my head. I assume something about maybe processor speed back then, because this thing is rooted in the 90s, and keeping track of the crankshaft, maybe a keep it simple, stupid type approach is what they were doing with that crank trigger versus a high tooth count, because processors weren't that advanced, and if you're going to have knock control and boost control and a bunch of things integrated that were basically rooted in the 90s, maybe that trigger pattern was what they selected. It has both a mechanical adjustment for the belt tension and a hydraulic tensioner. So it's a combination of these two devices that yield the right tension on the timing belt. This engine also came factory with a balance shaft that's been deleted, which is an interesting talking point. This engine has a larger than stock stroke crankshaft at 94 millimeters versus 88 millimeters. So Mitsubishi, when they developed the engine, they put a balance shaft in there. What that's going to do is balance the engine by canceling some of the harmonics that are naturally occurring in the rotating assembly. This little idler down here is remnants of the factory balance shaft system. Otherwise, it has a oil pump drive by the timing belt, and then just this idler pulley, an adjustable cam sprocket on the exhaust cam. But again, the real star here is the variable intake cam, because when you advance that intake cam during spool up, you widen the power band by getting the turbocharger online sooner. Some of the things that kept the 4G63 alive during its career as a OEM turbocharged engine is a fairly robust cast iron block. It has a lot of airflow available. If you look at the ports on the cylinder heads, they're big ports. You have rocker arms and hydraulic lash adjusters. So compared to something like a 2JZ where you have a camshaft lobe that's swiping a bucket, you're lift limited at that point because you don't have a rocker arm that's multiplying the lift. So, you know, rocker arm could be 1.5, 1.6, 1.9 ratio, and that really promotes a lot of valve lift that you just don't have present on a cam on bucket type arrangement. You also have the opportunity to be in an OEM turbocharged chassis that has a cooling system that was designed to manage the heat present from a turbocharged engine. So if you go back into, you know, say the Honda realm, none of those cars were engineered as OEM turbocharged vehicles. So they almost always had a deficient cooling system compared to the Mitsubishi Evo that had all these roots in rally racing, endurance racing. You know, this thing's got this big radiator on it, factory oil cooler, things that'll help keep the engine alive longer. Now, one thing that they did, which was a super good move, is a higher capacity oil pan. You know, you have a wet sump oil system. Once the engine speed is high, the oil is just foaming, frappuccino looking, and it's hard to get good quality liquid oil keeping the bearings alive. So anytime you can add oil capacity, you're adding oil life. So, you know, this has an old school AMS oil pan on it, which is gonna hold, you know, a quart or more oil, and that's gonna help keep that alive, because as that foam is on the top in the oil pan, you have more liquid oil present down at the oil pickup ideally, but the best way of ensuring that there's liquid oil available is adding capacity, whether it be a dry sump system or a wet sump system. Oil capacity is always your friend. So you have a couple things that are really working towards keeping this engine alive. Aside from the lower compression ratio, which we'll talk about more in a little while, just the fact that it's an OEM turbocharged platform and it had OEM engineering in terms of cooling, airflow, it just loans itself to being what it is. I mean, this is why these DSM platforms and Evo platforms have made so much power for such a long time. You know, its roots are in the late 80s, but for all that time, we were able to have so much fun because of a lot of this OEM engineering. Probably one of the biggest single takeaways that we'll get out of this engine is the lower compression ratio. You have to kind of imagine what the engine is going through when it's running, and the compression ratio is the first heat source. So when you're dealing with a modern vehicle that has a set boost level, like a modern OE/DI turbocharged engine, it's got a relatively high compression ratio because they have really good control over low speed combustion with the direct injection. And they are able to get away with a high compression ratio because they're, while running fairly high boost levels for a factory pump gas unit, they're managing combustion really well, and they're helping the catalyst live a long life. In the realm of what we are doing in the aftermarket, we're trying to have the most amount of fun for preferably the longest period of time, because it costs a lot of money to break your stuff. And one of the things that I dealt with Ronnie when he worked on my engine was he really was stuck on a low compression engine for me, because he said, you know, you're gonna win some races, you're gonna lose some races, but you're not gonna lose a race because you're missing 30 horsepower. You're gonna lose a race because you spun or you missed a gear or this or that. And you know, he explained to me this dance of compression ratio and boost and heat management. And basically, when you have a low compression engine, you have a very wide timing window. So the engine will run at a lower timing number or it will run at a higher timing number. And you're walking down essentially like a road that's around 15 feet wide. And as you raise the compression ratio, you narrow that road you're walking down. And you can get into engines that have a narrow window between not detonating and detonating. And you know, say if you had a 7.5 to 1 engine, you're walking down this big wide 12-foot wide road. And if you had a 10 to 1 engine, you're walking down a road that is maybe 4 feet wide. And then if you go into 11 to 1, 12 to 1, stuff like that, higher compression ratios that should really only be for methanol fueled engines, not gasoline or ethanol fueled engines. On gasoline or ethanol, you'll end up with a very narrow margin. And it's fairly unrealistic to think that the engine's going to live a long life with a very high compression ratio, because it's going to be knock prone. And it may not break right away, but you'll take the engine apart and you'll see the signs in the bearings and in the pin bores. Maybe you're bending rods. You know, there's different, in every community of engines, there's different types of failures. The Coyote guys will bend rods. Honda guys will, they'll crack blocks. Some of the super guys were able to crack, OEM 2JZ engines, and that's just from detonation. So when you're going through the process of building an engine, that last 20 or 30 horsepower that you'll yield from a higher compression ratio, it's not a zero cost to you because the engine lives for less time. So an engine like this, which it's terribly lazy off boost. I mean, it has 85 PSI of cranking compression because it's a low compression engine with big cams. And when you listen to it idle, it's just not happy at a very low speed. But when you get it up on the pipe, it has a big margin of error. And if you look at the timing map out of this car, you're talking about timing numbers in the high teens and low 20s, where a regular Evo may have 0 degrees at peak torque and 11 degrees or 12 degrees at high RPM. The engine is way more timing tolerant, and that gets into a whole voodoo of crank angle, combustion time, when do you light the charge, when can you maximize the force of the charge on the crankshaft to give you the most amount of power output. There's a lot that goes into it. But for the common guy that's just trying to have a good time, maybe we should reconsider low compression engines. If you blow your car up twice a year, it's a few months at a time to fix it, thousands of dollars to fix it, and you're not having any fun. And sure, you're in this process and maybe you're going through it for the first time and you haven't gotten tired of blowing it up yet. But if you're starting off and you're like, well, I want to make 1,000 horsepower, maybe you make 1,000 horsepower and you don't make 1,060 or 1,050 because you just build a low compression engine, and you get to have more fun with that engine over the years. This engine is presenting itself to us as you can have a lot of fun with a low compression turbocharged engine because it just lives well, so something to consider, especially if you're two-wheel drive. Your traction becomes the biggest obstacle, more so than power output. So, the Evos are special because they're all-wheel drive. Like I asked my brother the other day, like, could it use more power? And he says, yeah, it just doesn't really spin. Like, it's hard to make it spin. So he has a condition that's way different than, say, me with my Supra. My Supra won't eat much more than 1,000 horsepower on asphalt with the tires it has, so it doesn't make sense to ask for another 100 horsepower because I can't use it until I'm going over 100 miles an hour. Where this platform has got so much traction, it could eat it, but we're still not going to change the compression ratio. They told us that it's like 7-8 to 1, which is around where the 1G Mitsubishi engine was. And if those of you that were around for the 1G, you could tie the wastegate shut on your 1G Eclipse, and if you had a Cometic head gasket on it, you could just have fun. It just wouldn't break because it didn't have enough cylinder pressure and enough heat to pick at it. Versus a high compression engine, for those of you that have had a high compression turbocharged engine, it doesn't take much to kill it if the tuning is off. And again, it's different with methanol because methanol has the ability to remove so much heat Methanol is like coolant inside the cylinder versus gasoline and ethanol. You know, they just don't have that ability to suck the heat out of the program the way methanol does. So most of us that are going to be running ethanol or gasoline, lower compression is a strong consideration, should be a strong consideration over maximum power output. So the head studs that are successfully holding the head down with, you know, 45, 50 pounds of boost. Javi said they've run as much as 60 pounds of boost. This is an ARP custom-made 625. The 625 material is a fairly new material to the market. It has 37% more strength than a 8740 fastener. And it in this application, it has a bull nose. So you see this long area here that's gonna bottom out in the block. That keeps the stud from turning as you're installing the fastener and torquing it. So the bull nose bottoms in the engine, and now the stud can't turn anymore. So you could focus the effort during the application of torque of the fastener in just clamp force and not rotating the stud. Not all engines can use a bull nose. There are engines that say right below the last thread of the head stud is an oil galley, and if you put a bull nose on it and you go to and it's able to turn in there, you can crack the block into the oil galley. So not all engines get a bull nose, but this is a pretty nice fastener. The custom-made 625 also doesn't have any corrosion issues. L19 can get into hydrogen embrittlement, which if you read about hydrogen embrittlement, it's pretty fascinating. Water attacks the fastener in a way that under load, the fastener will just break. Whereas the custom-made 625, it's just not a problem. It's also not a problem with the common 8740 fastener, but in 8740, you give up that, you know, 37% more clamp load, which you need it when you're running this much boost. So, you know, if you're looking at fasteners and you're gonna buy fasteners for an engine that's gonna see a lot of boost, the 625 is more expensive, but it's cheaper than changing the head gasket after it's been running. This is very much how early turbocharged engines looked. You have a minimal amount of crown around the ring set because you need to have material around the ring set. You can't, it'd be impossible to move the ring set so far down in the piston. So you have this crown area around, but this big fishbowl is doing nothing but slowing the combustion down. So it would be hard to make this engine detonate. When you have an engine with a flat top piston and you look at like an in-cylinder camera of detonation, it always kind of happens at the fastest parts of the chamber near the quench pads, where when that piston's coming up to the head, there's so much speed of the compression of the charge that it loses control and it detonates. And you get into a big bucket, just a big bowl piston like this, it's really hard to make an engine like this detonate. So this is another good talking point. You know, once the multi-layer steel gasket came onto the scene, you know, there were 3-layer gaskets. And when you got into OEM turbocharged or OEM supercharged, those OEMs went to 5-layer and 7-layer gaskets. So the reason being is you have a chunk of iron and a chunk of aluminum, and you're trying to squish the gasket sealed with the minimal amount of deflection. And 5 thin layers of a gasket are easier to squish flat than a thick steel core and 2 outer layers. So when you get into gasket selection, if there's a higher layer count gasket available for your turbocharged engine, if you're using a multi-layer steel, always opt for the higher layer. So whether it be a minimum is going to be a 3-layer, but the 5-layer is going to be better for gasket sealing. Some of the later model GM stuff is 7-layer. And it just allows these thin shims to get very flat without a lot of deflection, because the least amount of deflection on the deck in operation is going to have the best gasket sealing, because you only have 3 or 4 thousandths worth of movement before the gasket will start to leak. So when they had this engine at a half-mile event years ago, they were able to make some coolant pressure, and what they're doing is they're exciting that cylinder head and that block enough that it's opened up past that 3 or 4 thousandths amount of sealing, and then you get into pressurizing the cooling system. And once you get past that point, now you're torching. And if you've ever seen the insides of an engine that had a multi-layer steel gasket that torches, it is destruction. So you don't want that. But if you're shopping for gaskets on your turbocharged engine, the higher layer count is worth your while. There's a reasonable amount of just water present in the cylinder. We're down here in Florida. The place is a swamp. The ethanol fuel basically draws the water in. So whenever you have an engine that's running on ethanol, and it's less of a problem on pump ethanol because pump ethanol has some gooey gasoline stuff in it, whereas race ethanol is a very dry fuel. So if you're using a race ethanol for periods of time, it's not a bad idea to fog the engine if it's going to sit for periods of time, or use some sort of top-end lubricant. It's not nearly as harsh as methanol in this subject, because methanol is really dry, and you'll create a lot of corrosion in bores with methanol. It's very corrosive fuel. Ethanol is kind of like really splitting the gap between gasoline and methanol. But there's some shadowing in the bores and some pitting in the bores that just, the thing sits, when it lived in South Florida, a lot of water in the air. Some of that ethanol down in South Florida, the pump ethanol, it actually kind of smells like water in the fuel, and that's because there's water in the fuel. But this is, some of this stuff here, it's not terrible, but it's just an age thing that you've got to deal with when you're using an alcohol-based fuel. But no heavy scuffing on these two cylinders, at least. Number 4 was the trouble cylinder. So what he ended up doing was, Tim was putting a spark plug in this thing every once in a while because it was fouling that plug. So we should be able to see more deterioration in number 4 than the other cylinders. Another thing that the Mitsubishi 4G63 had really going for it was oil drain back. So all of these big holes in the engine block are to aid in oil returning back to the pan. So you have a bunch of oil being pumped up to the top of the engine, and the crankcase pressure is trying to leave the crankcase and try to escape out of the valve cover. And there's just traffic. And if you have an engine that has inadequate drain back and crankcase pressure, the oil can get trapped in the head, and then it will deplete what's in the pan, and then the engine will burn up. And the early modular Ford engines were notorious for this, and the RB26 guys actually put external drains to drain oil back to the pan. And a lot of aftermarket engine builders will also add drains to the cylinder heads to return oil back to the pan. But Mitsubishi was ahead of that problem on this, and they have a lot of drain back available, because those big holes, these big holes that you see in the deck, if the holes are small, the crankcase pressure is coming up, the oil is trying to go down, the crankcase pressure will carry the oil out of the engine. And those engines are the ones that, you get a lot of oil in a catch can, things like that. Well, Mitsubishi, with these big holes, it just allows room for the traffic. So crankcase pressure is coming out, oil's going back down, oil pan stays replenished, oil pressure stays adequate, engine continues to live. So this is just a fundamental advantage you have in an OEM engineered turbocharged engine. There's some assorted stuff in the oil pump pickup. Looks like some silicone, and then some towel or rag, paper towel shreds probably, and a little tiny piece of metal. This little guy right there. That guy came from somewhere. Now this is fun. The oil pan was extremely tight to the engine, but the oil pump pickup tube is not. And that's a paper gasket that will compress over time. But when you're installing an oil pickup tube on an engine that has a paper gasket, make sure that you use the torque specs, because as that gasket compresses, the bolts will get loose and looser and looser and looser. And if you have a oil leak between the pickup and the oil pump, you're not going to be picking up oil any longer, and you'll kill an engine. There's also another bolt missing here the one that supports the tube, it's not there, unless it was here, because this bolt was in the bottom of the oil pan, but this one looks like it's freshly fallen out, and this one's just not there. But the oil pump pickup tube has a support bolt on it because the amount of vibration that's in the engine, if the oil pump pickup tube is not supported, it will likely vibrate, crack, fall off in the engine, and then you're back to not picking up oil. So this is the windage tray, and what this plate here is trying to do is keep oil that's in the oil pan cavity away from the parts that are spinning. Because when you pick up the oil, not only does the oil have weight, which you know, a lot of people get all jazzed up about having their pistons balanced within a gram. Well, I mean, oil weighs something, so as it's splashing around in the engine, you're picking up weight. So this windage tray is scalloped to evacuate oil to where the engine's spinning and is trying to spit the oil out of the rotating area back down into the oil pan. Second piece is a crank scraper. This is shaped specifically so the crank throws, counterweights, and the connecting rod can pass by it, and all that oil that's just in motion will hopefully hit this, drip onto the windage tray, and go back into the oil pan. So these are two things that are done in an attempt for better oil control because of the engine RPM. So another neat thing that the 4G63 has is this integrated girdle. So this piece that I'm touching is also the main caps. It's all one piece. This wasn't present on the early 4G63s. This is a 7-bolt and later approach. And not only do you have now integrated the main caps in one piece, but you're sharing the vibration that's going on in each main cap into this part. So this is a pretty neat piece. It's a big chunky piece, and we'll get off the car and look at it some more. But again, OEM turbocharged engineering, you know, like this evolved into a bed plate design. You know, the bed plate engines are stronger than this design, but this is what they were doing, you know, to keep these engines alive and keep them living and keep them managing all the power. Because even in its delivered form, Mitsubishi needed to have an engine that could be raced successfully in an endurance environment. And this is one of the steps they took to make that happen. So with the pistons on the bench, there's some stuff that's becoming evident. This has free movement, and I can reach in there and rotate the pin with my fingertips, and everything's free and clear. Then the other three are sticky. So you have bent pins. When the pin bends, it then won't rotate in the bore of the piston, and eventually will tear itself up or tear itself out. So this engine has 3 bent piston pins. The piston pins are fairly thin wall at 150 thousandths. This isn't something we would do today. One of the things you kind of have to understand about piston pins is the material is all fairly similar. So if you buy a set of Wiseco pistons or JE pistons or Manley pistons, the material is the material. It's a surface hardened pin that the manufacturer or engine builder will either ask for a longer pin, depending on piston design, or they will ask for a thicker pin, a thicker wall pin, to try to add material. Now the way to make that even better is if you move to something like a Bill Miller engineering pin or a trend pin where the pin is now through hardened. And what that does is it gives the pin a better memory. In operation, during operation, the pin may bend, but it will likely go back to its original shape, versus a pin that is just surface hardened like this pin. Once it bends, it stays bent, and you'll start to get into some material transfer, which you can see it and feel it on this pin. And again, the other pistons don't move freely. So where this one will just flop back and forth, this guy is stuck. So you got bent piston pins. The ring gap on the top ring was right under 30 thousandths of an inch, and the second ring was 32 thousandths. Now that's going to be something that a lot of you may feel some kind of way about, because it's a fairly big number. It's about 10 thousandths bigger than what a regular 85 or 86 millimeter bore would get, but the ring can never butt. And when it butts is when the ends meet, because the ring gets overheated because you messed up on your tune-up, and the rings touch and then the ring bends and now the engine's wasted. When you have a big ring end gap like this, not a lot of bad happens. This engine wasn't puking copious amounts of oil into the catch can. There's much more damage from corrosion in the bores that would promote blow-by than the ring gap itself. You guys may think that that's a bad move, but it's a great illustration of showing that when the gaps are big, nothing really bad happens. When the gaps are tight, the ring can deform and bend, and then you've got to take the engine apart. You know, the manufacturer recommendations are minimums. So when you look at the ring gap minimum, that's a minimum value. As you gain experience, you may open that clearance up. And again, not much goes wrong from that. There's a couple things going on as we move into the bearings, but they're mainly going to be focused on the crankshaft. The crankshaft is an Eagle crank. They were unsure of what the crankshaft was because the person that had sold it had labeled it as a custom, but it's just an Eagle crank. But when you look at the journals, on the rod journals, you can see that there's actually more wear present on the bottom side of the journal than the top side of the journal. Part of the crank that's seeing the combustion as the piston pushes up the bore to TDC. And this is the side of the crank that's just returning the piston back down to bottom dead center. And look at the wear difference on the top versus the bottom. Do you see the scratches and the discoloration? That's oil flow. And this crankshaft doesn't have direct oiling. So the oil enters the crankshaft through these two holes across the journal, and then it travels up and it tries to exit the crank rod journal horizontally, basically, and the oil gets trapped because of the centrifugal force of the engine RPM. At low engine speed, the way that this crank is drilled is fine. At high engine speed, the oil gets trapped in the crank. So a crankshaft like from Brian Crower that has direct oiling is a good move, and without any real debate about it, you can just look at the crankshaft and see that even though there's not as much load present as the piston goes back down the bore, the oil's depleted and the oil can't keep the bearing and the crankshaft separated. So that's something that may be changed because of the nature of the vehicle. This vehicle spends a lot of time between 5,000 and 9,500 RPM. So having proper oiling is a good thing. The center main has lost its crush. So this bearing is failed. This is a really neat topic because a lot of people are under the assumption that what's holding the bearing in place in the engine is the tang on the bearing, and that's not correct. The tang is there to locate the bearing during the installation of the bearing. The crush of the upper bearing and the lower bearing meeting in the housing bore and being pushed against the housing bore is what holds the bearing in place. Yes, this bearing has lost its crush, but it's because it's failed. So when you look at the surface of the bearing, it's given up, and it's given up in the center main because the crankshaft is whipping. It's changing shape in operation, which is power level, it's stroke, it's material, and it's probably just time to go to a different crankshaft for the use. Even though the crankshaft has lived a long time and the engine's lived a long time, if you are looking at something and trying to improve it, you wouldn't put a crankshaft back in that's seen this much fatigue work, because every time it moves, it's being worked on a very small level. So you keep working a part back and forth, eventually it's going to break. But you can see the damage on the crankshaft main from it whipping, and the bearing crush is gone. So this bearing still has crush. I have to push it down into the shell, and when I move it, it's tight. This one has lost its crush. It's closed up. So that thing is junk. But this problem isn't a bearing, it's not the bearing manufacturer's fault. This is just a use. So you have an engine that makes over 250 horsepower per piston. It's got over 25,000 miles of use. When you drive a car like this, it's because you're making rips. You're not driving it because it's fun to drive around. The trans is noisy, it's laggy off boost. It's got a lot of personality. It's a car that you take out, you do some rips, you go back home, you relish in the access to have a toy like this and just live in the smiles. But these parts have done a fair share of work over the years. So one thing that we'd consider is when we get the main girdle back on, without the bearings in it, is you'd measure that main tunnel and see if this main tunnel is larger than the other tunnels. Because when you get into that about a crank whip, it's working the material around the crank, it's working the block. So you want to make sure that you have control of the bearing housing, because control of the bearing housing and control of the crankshaft is going to make the most consistent hydrodynamic wedge of oil that's riding on that crankshaft, keeping the bearings from touching down on the parts, which is what we have here. If you look through either the rod bearings or the main bearings, they've all reached their service life. So again, they don't owe anybody anything, but they've definitely reached their service life. But this one was on the way out. This is where people get into saying a spun bearing, and it doesn't spin with force. It spins because it closes up. And when it closes up, it no longer has anything holding it in the journal, and enough material has worn away from the face of it that then it can start to turn. But it doesn't spin because of a tang problem. It spins because it's collapsed the bearing, it's worn out, it's reached the end of its life. So as you look at the cylinder head deck, you can follow the path of the sealing ring of the head gaskets, and there was no combustion leak, so the cylinder head gasket was not leaking. It is worth noting on the 4G63, due to the valve size and valve angle, when you're timing this engine, it's important that you don't just rotate the cams, because the valves can hit the valves and they'll bend slightly, and then shortly thereafter, you'll have a valve train failure, a catastrophic failure. So when you time a 4G63, you want to be careful that you're not running the valves into the valves. It's one of those engines, not only a piston to valve concern, but a valve to valve concern as well. Now forgive all the gunk, the kind of this discoloration of film, that's just from the oil that's being used. What you want to be focused on is you've got a chilled cast cam, it's a Kelford 280, and then you have this roller rocker arm. So we talked about it earlier, but you have a roller rocker arm, which is going to give you the opportunity to run more valve lift. And then there's a small hydraulic lifter on the 4G63 that will act as a cushion rather than be a solid valve train like on a Honda. So the valve train is pretty forgiving and pretty good on the 4G63. Also, in terms of serviceability, the head hardware is independent of the camshafts. So a lot of import engines, you have to take the camshafts out to get the cylinder head off. This one you don't. You can take the cylinder head off if you need to service the gasket. Because keep in mind, the origins of this engine were in the composite head gasket days. So if you were around for the 1G, Eagle Talon, Eclipse, they were just, the head gasket was the fuse. Instead of you hurting the bottom end or hurting the head, you just push a head gasket, and the way the valve train is arranged, you can quickly pop the cylinder head off, change the head gasket, go back to having fun. And as the engine evolved and the multi-layer steel head gasket evolved, kind of like took away that fuse to some degree. But in the terms of longevity, those early 1G DSMs, they had kind of the writing on the wall as far as what you can get away with, again, being a low compression engine. Now, low compression doesn't come without a cost. The engine doesn't run as well down low. It doesn't have that pop. It's not as crispy. It's not as snappy. It's not as efficient. So it does make for a bit of a doggy engine off boost. Again, this engine has 85 or 80 pounds of cranking compression. When you get into an engine that has 200 pounds of cranking compression, there's a bit of snap, and you'll feel it at that low speed. But at high speed, when the turbocharger is doing the major influence on how much power the engine makes, the lower compression just makes it easier to make the engine live. At the end of the day, really neat case of a low compression engine, 25 or 26,000 miles of just taking rips. I've driven this car before. It's really, once it gets on the pipe and you start pulling that lever, it's a really, really neat ride. Just as fun can be. So the car definitely serves its purpose, and the compression ratio and camshafts and tuning and everything loan itself to be a pretty reliable vehicle. So we're gonna take these parts to the machine shop. We're actually gonna follow this engine all the way through the machining processes. So if you wanna tag along for that process, we're gonna try to answer the question of what happens when you drop your engine at the machine shop, what you should expect, and what each step looks like. And the machine shop that's gonna do the block work has a very technical hone that will actually be able to see the deformation of the cylinder over time, because even though it's cast iron, big heavy chunk, the boost and the stress, it changes the shape of the components over time. So it'll be a neat opportunity to follow this engine through the rebuilding process, back here for assembly, back into the car. Appreciate you watching this video. Hopefully you've learned something, or it was interesting at a minimum. If you do enjoy this type of content, come over and watch my new channel. It's RS Garage. Just kind of getting things going, but we have a pretty good thing going on, and I'd appreciate your support. Thanks, and I'll see you next time.
Nothing missing. Better luck next time, Bob.
This thing went 190.
Yeah, but look, AC. Look.
Hold on now. Wait a second.
That's a custom shifter that I put on it.
Nope, doesn't
It's
count.
white.
It's not stick shift. I'm just kidding. That's awesome, man. Congrats.
Oh man, that's a rush, isn't it?
Oh my god, I love it.